Assalamualaikum and welcome back. Now let's look at example concerning conservative field. Okay, here we have a question. It says, show that f dot dr along curve C is independent on its path. Hence, find a potential function and evaluate the line integral along C, where here we have a vector field f and C is the line segment from point 0, 0, 0 to point 1, 0, 0, then to 0.110, and then to 0.111. Okay, so it has many parts here. We want to show that f dot dr is independent on its path, meaning that we need to show that f is conservative, because when f is conservative, f dot dr does not depend on its path. Okay, so that would be the first task that we need to do. Okay, and then here we have, we also are asked to find the potential function. So if f dot dr is independent on its path, independent of its path, then f is conservative. So when f is conservative, there exists a potential function, and we can use that potential function to evaluate f dot dr. Okay, now let's, we need more room. Okay, so here we have our question. So this is our vector field f. The first part is we need to show that f dot dr is independent on its path. So what we need to show is need to show that vector field f is a conservative field. Okay, because once f is conservative, straight away we know that f dot dr is independent on its path. Okay, so to do that, we need to show that f does not circulate. So when f does not circulate, then f is conservative. So to show that f does not circulate, we need to find del cross f, which is the curl of f. So curl of f is really the determinant of a 3 times 3 matrix. The first row are the standard unit vector. Second row would be the components of del, which is partial x, partial y, partial z. And in the third row would be the components of f, which are 3x squared, 6y squared, 9z squared. Okay, so we need the determinant of this. And remember the sign alternate, plus, minus, plus. Okay, some of you can do this very quickly. All right. Okay, so for the x component, we cross out first row, first column. So that will give us partial y of 9z squared. So that is 0, minus partial z of 6y squared. That will give us a 0 as well. Okay, and then we have negative sign. Now for the y component, we need to cross out first row, second column. Okay, and then get the determinant of the 2 times 2 matrix. So here we have partial x of 9z squared. Obviously that will be a 0. Okay, and then minus we have partial z of 3x squared. Definitely that is also a 0. Okay, now the z component. For the z component, the sign is positive again, and then we need to cross out first row, third column. Okay, so for third row, cross out first row, third column, we get 6y squared, differentiate with respect to x. That would give us a 0. And then we have 3x squared, differentiate with respect to y. That is also 0. So here we have a 0 vector. You can write it this way, or you can write 0 vector. So f is conservative, right? So there is no circulation. Oops. Circulation in f. Hence f is a conservative field. So for conservative field, f dot dr, that's ugly, hang on. Hence f dot dr is independent or does not depend on its path, or you can say is independent of its path, or you can say does not depend on its path. Okay, so that is part 1. We just showed that there is no circulation in the vector field f, hence f is conservative. So when f is conservative, f dot dr is independent on its path, or you can say f dot dr integrate over curve C does not depend on its path. Okay, so now the second part. If f is conservative, then we know from the properties for conservative field, there exists a potential scalar phi such that f is equal to the gradient of phi. Okay, so we want to find phi now. Okay, so there's a potential function such that f is equal to the gradient of phi. Okay, let's say let phi equals, well, phi is going to be a function of x, y, and z. So we need to find the function or the scalar field. Scalar function phi is, let phi is a potential function. Then f is going to be equal to the gradient of phi, which is partial phi partial xi plus partial phi partial yj plus partial phi partial zk. So here we have vector field f, which is equal to what is it, 3x squared I, 3x squared I plus 6y squared j plus 9z squared k, and this is equal to the gradient of phi, which is this. Okay, so two functions are said to be equal if and only if the components are equal. So from here you can say that partial phi partial x must be equal to 3x squared, and the y component should be the same as well. So partial phi partial y must be equal to 6y squared, and the z component, partial phi partial z, must be equal to the z component of f. So our task now is to find the scalar, the potential function phi. Okay, so let's say you use the first equation here. I'm going to call this first equation, second equation, third equation. So this one is second. Alright, so let's use the first equation. We have partial phi partial x. We want to find phi. So from phi, from partial phi partial x, what we need to do is we need to integrate partial phi partial x with respect to x. So partial phi partial x is equal to this. Okay, so what we're going to do is we're going to integrate that. So when we integrate 3x squared with respect to x, we get x cubed over 3. 3 over 3 is 0. But of course, the function phi is in terms of x, y, and z. So we have, instead of adding a constant, let's add a function. I'm going to call it g, a function of y and z. Because when you differentiate a function of y and z with respect to x, you get a 0. Okay? So that is from integrating the first equation. So now we're going to do the same, but we're going to use the second equation. So to get phi from the second equation, we need to integrate with respect to y. So partial phi partial y here is equal to 6y squared. So we're going to integrate that with respect to y. So that will give us y cubed over 3. 6 over 3 is 2, and then instead of adding a constant, let's call this g2 of x and z, because I'm going to call this g1. Okay, g2 of x and z, because when you differentiate a function of x and z with respect to y, you get a 0. Okay, All right, we're going to do the same thing using the second equation. So to get phi from the third equation, we need to integrate partial phi partial z with respect to z. So partial phi partial z is this. So now we're going to integrate this with respect to z. So we have z cubed over 3, 9 over 3 is 3, and then add a function in terms of the other two variables, which are y and z. Okay, so the next part is to put them together. So the potential function is, all right, so we're gonna potential function, oh dear, can't even spell function now. Okay, so now the next part is just putting them together. Remember, if you see the term twice, just write it once, okay, because these are all the same. So this is phi, this is also phi, this is also phi. All of them are the same, okay? So you just put them together. So from the first one we get x cubed. We don't have x cubed in the second one or the third one, but it is embedded in here, okay? That's ugly. Okay, and from the second one we have 2y cubed, okay? It doesn't have 2y cubed in here, but it is embedded in g1. It doesn't have 2y cubed in the third, but it is embedded in function g2, okay? And we have 3z cubed. We don't have 3z cubed in the first one, but it is embedded in function g1, and it is not in in the second equation, but it is embedded in function g2. Okay, so what you do is you just put all the terms together only once. Okay, so this is our potential function. So that is part 2. Now for part 3, we are asked to evaluate f dot dr, where c is line segment. So we have many line segments here, from 0.000 to 0.100, and then to 0.110, and then to 0.111. So if we want to use line integrals using regular property, how many line segment we have to do this? Okay, this is going to be like a piecewise line integral, piecewise curve, like this, meaning that we have to evaluate on each curve and then add them together. But f is a conservative field, so we don't have to do that, because what you need to do now is just use the fundamental theorem, where you only need the initial point and the destination point. So the starting point and the ending point. It doesn't matter how many stops it makes in between. You just use the initial point and the destination point, and of course our potential function. Okay, so we're going to use the fundamental theorem for line integrals. So my goodness, all right. So the fourth part is we need to find f dot dr along curve C. We have many points, but we don't have to use all of them. All we need is the initial and the starting point. So the initial point would be this. So this would be our A. And it doesn't matter how many points it stops in between. We just use the initial point and the starting point. So the initial point is the origin, and the destination point is at point B, 1, 1, 1. So this, oopsie, we're going to use the fundamental theorem. So we're going to use the destination point, end point, minus phi at the initial point, which is at 0, 0, 0. So this is our phi. Okay, so we're going to use this instead of evaluating the line integral. All right, so phi at 0.111 would be 1 plus 2 plus 3 minus phi at at the origin, which is 0, 0, 0. Not very professional there. So from here we get this is equal to excuse me, 6. Okay, so f dot dr for the line segment, along the line segments, we have many stops, but we don't have to evaluate the line integral. We just use the potential function. Okay, so that is one example concerning conservative field. Thank you.